Hi everybody. Chapter 4, Atoms and Elements. If you haven't already done it, it's a good idea to print the periodic table that I linked to at the top of the homepage, and I'll try to add it to this module too, because you'll want to be able to look at the periodic table and potentially make notes on it while you're watching the lecture. Okay, so atoms and elements. Elements and symbols. Elements are pure substances, we learned that last chapter, from which all other things are built. They cannot be broken down into simpler substances other than doing nuclear chemistry. Examples of elements and their names. Many of them have the same name as, or same symbol as the first letter of their name, but not all of them. So uranium is U. Source of the name is the planet Uranus. Iodine, I. Magnesium, curium, Cm. Copernicum, Cn. Those are not the most common elements that you'll see. Some elements have one-letter abbreviations like carbon, nitrogen, and fluorine, and oxygen. However, some have two: cobalt, calcium, aluminum. And that's most likely because another element already has that first letter. Like, for example, cobalt, the C is taken by carbon. Now, it's important to note that the second letter in the symbols is always lowercase. So first letter uppercase, second letter lowercase, because if you were to write CO with two uppercase letters, that would not mean cobalt, that would mean carbon monoxide, because it would represent one carbon atom and one oxygen atom. So here's a list of common names and symbols. I do not expect you to memorize these. If you look at the periodic table that I provide on the home page, this is the same one that you'll have during exams, and the names of the elements are on that periodic table. However, the more familiar you will get with it, the better off you will be during the exam time if you are not having to look up things or find them. So a lot of the symbols come from Latin names. Gold is AU and silver is AG from argentum and aurum. Write the correct chemical symbols for the following. Iodine. So you can pause and look at this for practice. Pause the recording, and then when you're done, start it again. Okay, so for iodine, it is I. For iron, it is Fe. For ferrous, magnesium is Mg. Zinc is Zn, and nitrogen is N. Okay, I'm going to skip those. You can practice those. So again, learning check 2, give the names of the elements with the following symbols. Go ahead and pause, write the names down, and this is good practice for getting familiar with stuff. And then when you're done, hit play again. Here are the answers. Okay, so this is the periodic table. It's an organization of the elements, and it's pretty. The more you learn about it, the more amazing it is. So the periodic table has one box for each element, and they go in numerical order, starting at 1 on the top left, and the numbers go across. 2 is here, 3 to 10, then 11 to 18, then 19, and so forth. Notice that that there are names at the top of each column. And I should point out that each column is called a group. So columns are groups, and it turns out that chemicals they behave more chemically similar when they are grouped within a column or a group. So for example, let me see if I can get it. So for example, potassium and sodium behave more alike than potassium and calcium. Oxygen and sulfur behave more similarly than oxygen and nitrogen. Okay, so we're going to look at the periodic table in more detail. So groups and periods. So like I said, the columns are called groups. The periods are the rows. So period 1, period 2, period 3, and so forth. Group numbers are written at the top of each vertical column, and they also have names. So there's a couple different naming schemes for the numbering of the groups. So the first one was 1A, 2A, and then we skipped this block called the transition elements 3A, 4A, 5A, 6A, 7A, 8A. Or the other scheme is without the letter, it just goes numerically across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13 to 18. Those are the groups. And then some of the groups have names. So see here, alkali metals is the first group. Alkaline earth metals is the second group, or group 2A. I used to have a hard time keeping track of which was alkali and which was alkaline earth, but the second group has 2 words in the name instead of 1. Then I finally could remember it. So alkali in group 1, alkali earth. No common names for these, but halogens are 7A, and then the noble gases are 8A. And this group in gray in the middle, those are collectively called transition elements. So the alkali metals are the elements in that first row, their first column, and they are very reactive. I have this funny recollection from high school. My high school chemistry teacher, who was also my basketball coach, used to do a demonstration with sodium. Sodium metal, surprisingly, because sodium is what's in, the sodium ion is what's in table salt, but sodium metal is a soft, shiny metal. It's so reactive with water that it has to be stored under oil. And for a fun demonstration, my high school chemistry teacher used to react sodium with water on the bench top. And he said that one year he had a little bit too much sodium and it reacted and it hit the ceiling. And so he had sodium stuck on the ceiling. And he continued on the rest of the day with his classes. And during the course of the day, little bits of sodium were falling off the ceiling tile and collecting in his hair. So that night, he went home, and when he was taking a shower, the bits of sodium that had fallen into his hair started reacting, if you can imagine. So that is my visual for remembering how reactive the group 1A elements are. The alkaline earth metals, they're in the second group, and they include beryllium down to radium. They're not as reactive as the 1As. They like to have 2+ charges. Halogens are in group 7A, and they are characterized by mostly being in the gas form, and also they are fluorine through iodine. They are all diatomic, naturally occurring, meaning there's 2 of them. They move around in units of 2. So like 2 spheres, any of these, if you saw them, they would mostly be a gas and moving around in units of 2. Those are the halogens. Okay, so identify the element described by each of the following groups and periods. What's going on here? Let me look. Okay, so this first one this is actually multiple choice. So look on your periodic table, look for group 7A and period 4. And so that is going to be in the halogen column and in the fourth row, and the answer to that is going to be bromine. Look in group 2A, so that is an alkaline earth metal in the third period, and that's the third row, that will be magnesium. Group 5A, second period, so second row, group 5, and look on your periodic table, and that will be nitrogen. This is part of why I say it's helpful to have the periodic table nearby. Okay, so look on your periodic table around boron. Sorry, B is boron, and you should see a staircase of a thicker line. And if you have a color printer, I think it might even come out red. This staircase, that is the dividing line between metals and nonmetals. It might be slightly surprising that all that stuff to the left are metals. So sodium is a metal, it's way over to the other side, and the nonmetals are in the top right. The elements that run along that staircase, those are metalloids, and so they have some characteristics of metals and some characteristics of nonmetals. And for that reason, some of these have been used as semiconductors, like silicon and germanium. Those have use as semiconductors. Okay, so metals, except for hydrogen, are located to the left of that that staircase, and they tend to be shiny, ductile, meaning bendable. They are good conductors of heat and electricity. They are solids, except for mercury, which is a liquid. Nonmetals are on the right side of the periodic table. They tend to be dull, brittle, and insulators, poor conductors, but good insulators, and they have lower densities and lower melting points. Metalloids, metalloids exhibit properties of metals and nonmetals. They're better conductors than nonmetals, but not as good as metals. So for that reason, they're used as semiconductors and insulators. Okay, so here's a table summarizing characteristics of a metal, a metalloid, and a nonmetal. And notice the metal has a density of 10.5, the nonmetal 2.1. The melting points aren't showing up here, but the melting point for silver is 962 degrees C, and the melting point for antimony is 630 degrees C, and the melting point for sulfur is 113 degrees C. Okay, so go ahead, look on your periodic table and identify each of the following elements as metal, nonmetal, or metalloid. So remember, to the left of the staircase, metal, to the right, nonmetal, on the staircase, metalloid. So pause this and then go ahead and do that for practice. Okay, and when you're done, go ahead and start the recording again. And here are the answers. Probably the most famous metalloid is silicon because of its semiconductor properties, and I would say second most popular is germanium. Okay, so which of the following elements match the description? Metals in group 4A. So you're going to look at 4A, and that would include SN, which I think is tin, and lead. Nonmetals in 5A, those are going to be nitrogen and phosphorus. metalloids in group 4A, silicon and germanium. Okay. Chemistry linked to health. I know a lot of you have interest in this. So of all the elements, 20 are essential for the well-being and survival of the human body. 4 of them make up 90%, 6% of the body mass, and it wouldn't probably be too hard to guess which 4 those are: oxygen, nitrogen, hydrogen, and carbon. Most of our hydrogen and oxygen is in water, which is 55 to 60% of body mass. There are also macro minerals: calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium. They are involved in the formation of bones and teeth, maintenance of heart and blood vessels, muscle contraction, nerve impulses, and acid-base balance of body fluids, and important in the regulation of cellular metabolism. So those are boxed. Micro minerals, ones that are used in needed in lower quantities, those are in the purple box. Those are the trace elements: copper, zinc, vanadium, chromium, molybdenum, iron. I was kind of surprised iron's a micro mineral. Okay, the atom, 4.3. The atom is the smallest particle of an element that retains its characteristics. Aluminum foil contains only atoms of aluminum. So we're going to go over, for a lot of this, I will probably skim the experiment descriptions and just want to make sure that you know the results, the conclusions of what we learned from these experiments. So Dalton's atomic theory, this is important though, you want to know these, is that atoms are made of tiny particles of an element are similar to each other and different from other elements. Of 2 or more different elements combined to make compounds. So if you have something that has an atom of hydrogen and an atom of carbon, that is a compound. And they are rearranged to form new combinations in a chemical reaction. Atoms are never created or destroyed during a chemical reaction. We know that atoms have charge. And there are the subatomic particles that make up atoms. So by subatomic, we mean smaller pieces, sub, of the atom, atomic. There's 3. There's the proton, those have mass and they are positively charged. Electrons, which we consider to be massless and they have negative charge. And neutrons, which have no charge but do have mass. Remember that like charges repel and unlike charges attract. So one important experiment that led to a greater understanding of the architecture of the atom, how these subatomic particles are arranged, was J.J. Thomson's cathode ray experiment. So these cathode rays, which are essentially electrons, he realized that they are particles, which we now know as electrons, that are much smaller than an atom. And he had originally thought that the atom was arranged with what was called the plum pudding model, where there were what would be raisins in plum pudding. He thought that protons and electrons would be randomly distributed in a large cloud. That would be the structure of the atom. Here we go. Better drawing than mine. So we have this positively charged pudding and negatively charged atoms, electrons scattered throughout. But Rutherford's gold foil experiment showed that this was not the case. So he made a really, really thin foil of gold, like only a couple atoms thick, and then he bombarded it with what were alpha particles. They're like helium, a charged helium atom. And the expectation was that the alpha particles would pass through part of the time and bend. But what he found out was that, let me see if there we go. What he discovered, so here's the detector. Here's the thin foil. This is the generator of the alpha particles, and he's bombarding the thin foil with these alpha particles. And when they hit something that's not dense, they pass through. If they come close to something dense, the path of the particle bends a little bit, and if it hits something square on, it bounces back. His expectation was that all alpha particles would pass through the gold foil. And what he found was the vast majority of the time they passed through, but occasionally they would bounce back. And this was not expected at all. In his terms, this would be like, or I've heard this metaphor before, this would be like aiming a cannonball at a piece of tissue paper and having the cannonball bounce back at you. The density of what the atom was, they thought would be analogous to the tissue paper relative to the alpha particle. And so what he learned is that there must be some really dense concentrated particles in the atom that have all the mass. And that because the vast majority of the alpha particles pass through undeflected, the atoms are mostly made up of massless space. And so that led to the hypothesis, or the thought, the idea that the structure of the atom consisted of a nucleus located in the center of the atom that contains protons and neutrons and most of the mass of the atom. The electrons occupy a large empty space around the nucleus. And so here is a little map of a lithium ion. And so lithium has, I need to have my periodic table next to me. Lithium has 3 protons, and this one has 4 neutrons. And all of those are located in this nucleus. It has 3 electrons, which counterbalance the 3 protons, but they move in a much larger region of space. Now this is showing it as a circle, but remember, atoms are in 3 dimensions, so this is actually a sphere. So in an atom, the protons and the neutrons that make up almost all the mass are packed into this tiny volume. We call that the nucleus. The rapidly moving electrons surround the nucleus and account for the vast majority of the volume of the atom. Because the mass of subatomic particles is so small, chemists use a very small unit of mass to describe them. Those are called AMUs, or atomic mass units. And this is kind of a mess. Let me see if I can clean this up a little bit. Okay, so the 1 atomic mass unit is equal to 1/12 of the mass of a carbon atom that contains 6 protons and 6 neutrons. You may, if you talk about proteins, you'll see Daltons. 1 atomic mass unit is 1 Dalton. I really only hear Daltons talked about in terms of proteins mass. Electrons have a very small mass that they're not usually included in the mass of an atom. Okay, so this is a summary of what we've learned from these experiments about these 3 particles that make up the atom. The proton which has the symbol of P or P+, and you can also see H+. You guys won't really understand why now, but I'm just going to put it here so you have it in your notes. The neutron. So the proton has a charge of +1. It has a mass of basically 1.007, but 1 is good enough for us for most of our purposes. And it is located in the nucleus. The neutron has the symbol N or N0. It has no charge. It also has a mass of basically 1, and it also resides in the nucleus. So these two particles make up that very dense nucleus that caused the alpha particles to bounce back. Electrons have the symbol E minus. They have the symbol or the charge of 1 minus. And when you round to 1 sig fig or 2 sig figs, the mass of the electron is essentially 0. So for our purposes, our masses are 1, 1, and 0. And it is located in this diffuse cloud outside the nucleus. Which of the following subatomic particles fits each of the description below? Found outside the nucleus. Has a positive charge. Has mass but no charge. Take a moment and answer. Pause. And then here are the answers. Okay, atomic number and mass number. All of the atoms of an element have the same number of protons and the same atomic number. So basically, if you know the number of protons in an atom, you can identify which element it is. So the atomic number is a whole number specific for each element, and it is the same for all atoms of that element, and it is equal to the number of protons in that atom, and it appears on in the symbol on the periodic table. So all sodium atoms have 11 protons, and that is the atomic number. They actually may have different numbers of neutrons. So just to emphasize, every hydrogen has 1 proton. Every carbon has 6 protons. Every copper atom has 29. And so you can find them in the periodic table in each box. Atoms are neutral. So unless specified as an ion, they are neutral. And the only way that that can happen is if the number of protons is equal to the number of electrons. So aluminum has 13 protons, and in order to have a net charge of 0, it has to have 13 electrons. So all aluminum atoms have 13 protons and 13 electrons. Okay, so go ahead and look on the periodic table and see if you can find each of these elements and write down the atomic number. Pause it here and then also write down the number of protons and the number of electrons. Pause it here, take a minute to do that, and then start up the recording again. Okay, so if you look on the periodic table, the atomic number for nitrogen is 7. And the atomic number for zinc is 30. And the atomic number for sulfur is 16. And we always know that the protons is equal to the atomic number. They are the same. And we also know that if they are neutral, which we assume all elements are unless otherwise told, then the number of electrons is equal to the number of protons. Now we have 2 particles that make up mass, right? It's the neutrons and the protons. So that will give you the mass of an atom. Now, all atoms of a particular element have the same number of protons, but they can have different numbers of neutrons. So atoms of an element with different numbers of neutrons are isotopes of that element. So restated another way, an isotope is an atom of an element with always the same number of protons, but different numbers of neutrons. So here are some examples. Composition of some atoms of different elements. So, and these are probably the most common isotopes. So hydrogen has the symbol H, atomic number of 1, because remember that's the number of protons. It has a mass number of 1. So from that, we know if the atomic number and the mass number is the same, that means that there's no neutrons, which is 0. And hydrogen's the only element that has that. And it has 1 number of protons and 1 electron. Nitrogen, it has an atomic number of 7, therefore it has 7 protons, and it's also going to have 7 electrons. The mass number for this isotope is 14. And remember, this is N plus P. And so we know that the number of neutrons is going to be 7. And we get this column by taking the mass number minus the number of protons. You will be given examples, and there's a quiz, examples of tables with some of the entries missing, and you'll need to complete them. So you want to know how the numbers are arrived at here. So gold has an atomic number of 79 and a mass number of 197. That means that the number of neutrons is going to be 197 minus 79, and that comes out to 118. So again, number of protons equals the atomic number. Number of protons plus neutrons equals the mass number. Okay, an atom of lead has a mass number of 207. How many protons are in the nucleus? Okay, well, so what I would do is go look on the periodic table and find lead, Pb. It is atomic number 82, and because it's atomic number 82, it has 82 protons. How many neutrons does it have? Well, it's going to be the mass number minus the number of protons, and that is going to be 125 neutrons. And the number of electrons is going to be the same as the number of protons, so 82. Okay, so isotopes and mass. Okay, so this is one way of denoting an element of a specific isotope of an element. This is magnesium. We know that from the symbol. This number is the atomic number, which is actually redundant, right? If we know that this is magnesium, we know that the atomic number is 12. And the number on top is the mass number. So that's going to be the number of neutrons plus the number of protons. And many elements have different naturally occurring isotopes. Okay, I think this is kind of overkill. Okay, so if you are given 018, 016, P31, and zinc 65. Calculate the number of neutrons. So this is going to be 16 minus 8 equals 8. 31 minus 15, that's 16. 65 minus 30 equals 35. But notice, if you go look on your periodic table, the mass you see is not an even number. It's 24.3. And that is because in nature there are multiple isotopes of magnesium that occur. And if you look here, this is showing you there's 3. Magnesium 24, that's the major one, and that's why the mass is closest to 24. Magnesium 25, which accounts for 10%, and magnesium 26, which accounts for 11%. So the mass that you see on the periodic table is a weighted average of these 3 isotopes. We count the relative abundance of that isotope more depending upon the percentage. So we have 3, roughly what's going to happen is we have 3 isotopes. They are mass 24, 25, and 26. Well, if you multiply by the relative abundance in a decimal form, 0.1013 times 0.117, these are the percentages divided by 100. And if you add them all together, you will get 24.3. Okay. Oops. Oh, and it's worth pointing out, so the symbols for the isotopes are written like this, with the superscript preceding, 25, magnesium 26. They can also be written that way, and we say the name this way. So magnesium with a mass of 24 is magnesium 24. Magnesium with a mass of 25 is magnesium 25. Naturally occurring carbon consists of 3 isotopes. Carbon 12, carbon 13, carbon 14. State the number of protons, neutrons, and electrons. Okay, well, so we know that because it's carbon, its atomic number is 6, and so the number of protons for all are 6. The number of neutrons is going to be this mass number minus the atomic number. So the neutrons are 6, 7, and 8. And in all cases, the number of electrons is going to be equal to the number of protons. A little bit about each of these. Carbon-13 was used in my type of spectroscopy. It's a stable isotope. It's in small abundance, but it has nuclear spin. I did nuclear magnetic resonance spectroscopy for my research. Carbon-14 is radioactive and it has a very, very long decay time. Forget exactly what the half-life is, but because of that, this is the isotope that is used for carbon dating. If you want to know how old something that is organic in nature, you look at the amount of carbon-14 in it relative to other isotopes. Okay. Write the atomic symbols for atoms with the following subatomic elements. Okay, 8 protons, that's going to be oxygen. And the number of protons plus neutrons is 16. 17 protons, that's chlorine. And 17 plus 20 is 37. In your book, they'll show also having the atomic number. I don't usually bother with that, but you should know what it means. 47 is silver, and 47 plus 60 is 107. Okay, which of the following pairs below are isotopes of the same element? X, 8, 15, X, 7, 15. Well, these have different numbers of protons, so these are not isotopes. X, 6 and 12, X, 6 and 14, X, 7 and 15, X, 8 and 16. So the only pair that both have the same number of protons is this one, and that's going to be carbon. And those are isotopes of carbon. Okay, calculating atomic mass. And this is what I was referring to before, but they'll have a worked out example here. Okay, so again, we look at chlorine and, oops,